Hello, and welcome to Science with Mr. Morgan. In today's episode, we're going to talk about objects in motion. First up, let's look at motion. So what is it? By definition, motion is just a change in position. Position refers to the location. Here, 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 they're all different positions. When talking about objects in motion, there is something known as frame of reference that we should talk about. And this refers to something that is not moving with respect to an observer that can be used to detect motion. And a good example of this is when you're on a school bus driving down the road. You, as well as the other kids on the bus, are not moving, meaning that you're not up walking around. If you look at stuff outside of the window, like a house, everything else appears to be moving. And this lets you know that you're moving even though you aren't moving directly. That is frame of reference. Anywho, let's look at distance. Distance is the length of the route between two set points. In track and field, there are a variety of running events, and one example is the 100-meter sprint. The distance of this event is, just like the name suggests, 100 meter. Notice that I mentioned meter. The SI unit for distance is the meter, which is represented with a lowercase m. Just like with other SI units, though, different prefixes are used to change the unit itself. Short distances use centimeters, which is represented with a lowercase c, lowercase m. Long distances use kilometers, which is represented with a lowercase k, lowercase m. Now, maps are a tool that can be used to measure distances. But, Mr. Morgan, how can a map that's on a single piece of paper be used to measure long distances? Well, maps have a little thing on them known as a scale, which can be used to measure distances between points on the map itself. A certain length on the map is equivalent to a certain distance in the real world, and you can use that scale to determine how far away 2 points are in the real world from the piece of paper. But enough about that. Now on to direction, which is an important component of motion. You have things like relative directions, which include up, down, in, out, forward, backwards, sideways. But there are also cardinal directions, which are north, south, east, and west. And these are indicated with a compass rose on maps and tells people where to go. That being said, we have now talked about both distance and directions, which means that we can say that we've talked about vectors. So what exactly is a vector? All it is just a measurement that has both size, aka distance, and direction. And these can be represented with arrows. In this case, the length of the arrow is the distance, and where it is pointing is the direction. And these can be used to represent both distance and direction of motion. Moving on though, let's look at speed. Speed is how fast or how slow something moves. It also determines how far something travels in a given amount of time. Due to this, the SI unit for speed is meters per second, represented with an m/s, both lowercase. When you're traveling, like in a car for example, do you travel at the same speed the entire time? No. There are different speed zones that you speed up or slow down in. Overall though, you have what's known as an average speed. And this average speed is calculated using the formula speed equals distance divided by time. Distance or time can also be calculated by rearranging the average speed formula for distance or time instead. Now, speed is constant but can vary moment to moment. What the heck does that mean? We've already talked about this somewhat with the car example I mentioned a minute ago. This means that the speed you are traveling at will always be the same at that particular speed, aka 60 kilometers per hour will always be 60 kilometers per hour. And we mentioned average speed, but there is also something known as instantaneous speed. And this is the speed at any given moment, which is much more difficult to calculate than average speed, because average speed is the average of the entire time. So if I said I traveled 60 kilometers in an hour, my average speed would be 60 kilometers per hour. But does that mean that I traveled 60 kilometers the entire hour? I mean, maybe if I'm on a highway with traffic that doesn't stand still, but if I travel 60 kilometers from town to town, I'm going to go through various speed zones. So my instantaneous speed will vary throughout because I will not be traveling 60 kilometers per hour the whole time, but my average speed shows that I traveled 60 kilometers within 1 hour. Now that we've talked about speed and direction, though, we can talk about velocity. Velocity is the measure of both speed and the direction, and therefore it's also a vector measurement. Now, while using an arrow to represent velocity, the length of the arrow is the speed, and the way the arrow points is the direction. The SI unit for velocity is a little different than others because it's meters per second and the direction it's traveling. That "and" is a big piece of it. Objects have the same velocity only when moving in the same direction at the same speed. This means that if the speed's different, they have different velocities. If the direction is different, they have different velocities. Now, the average velocity is calculated using the formula velocity equals distance divided by time. Wait a minute, this is the same formula as average speed, isn't it? It is, but the difference here is that velocity includes direction in the answer. Let's look at this image example together. Vector A and vector B are traveling at the same speed but in different directions, so do they have the same velocity? No. Vector A and vector C are going in the same direction, but at different speeds. So do they have the same velocity? Also no. Vector B and vector C are going in different directions at different speeds. So do they have the same velocity? Once again, no. Remember, to have the same velocity, they have to be going the same speed and in the same direction. Now, the last thing that we're going to look at today is acceleration. And this is the measure of the change in velocity of a moving object. Basically, it measures the rate at which velocity changes. Now, it's important to recognize that acceleration is an increase in speed, but it can also be a decrease in speed. And negative acceleration, aka a decrease in speed, is also known as deceleration. Now, aside from speed, acceleration can also be a change in distance without a change in speed. And when you experience acceleration, you may be able to feel the changes in the speed or direction. Have you ever been in a car with someone and they accelerate or brake quickly? You might have felt yourself move forward or backwards in response to that. Or if you're going around a turn, you are changing your acceleration and you might notice that your body shifts with that turn as well. When you calculate acceleration, you use the formula acceleration equals change in velocity over change in time. This weird little triangle symbol for change. Now, in these calculations that we talk about, it's important to note that the direction is not changing. Now, just like other things that we've talked about today, acceleration has its own SI unit. It is meters per second squared. And that brings us to the end of today's lesson. Until next time.